T divided by 2 times T times A. Okay, I try to use the same symbol as you will see in our textbook. In the textbook using a very special symbol A. And here I would explain here the T is the torque and T is the right? Let me double check. See, I have a title. Can I borrow your pen? Because T is varying across the whole thing, this is constant, this should be Q. And A, I'm going to define this one later. So that is the second equation. This equation basically tells us is we will be able to calculate the string stress. The string stress, and again I try to draw very generic. So this is the shaft. Okay, and that's the cross section. Can I modify this? Which one?
Is that tau? Q?
Q. That should be this one. And so Q equal to tau T. Okay, so that is the equation we can use. Okay, so that is the one. Sorry.
Oh, that's how
Sorry
you got
this
like
one.
the
Yes,
T.
yes, yeah. So my original writing is correct. Can I borrow your pen again? Thank you. So that is the equation we can use, and T is a given, and A is a certain quantity that is a constant as long as we are given the dimension. So basically A is a dimension related.
Not material related?
Okay. Okay, so from here you can see we can fix, if we are given a torque, and the torque is taking that direction, so if we apply the torque in this direction like this, so basically the right hand side of that is a constant number. So once we have a constant number, then you can see as long as we can determine a thickness, then right away we will determine the associated string stress there. Okay, so that is the goal. So basically the second property is tell us we know the Q is a constant. What is that constant number? So that is the second property we can do about this one. And how to do this one, and that's a little bit simple derivation here. So assuming we say we pick anywhere, so pick any here. So here is the T thickness. We need to put down to outside here. So to there is a T, and we know that string stress is basically everywhere here. So this is tau. And right now, what I want to do is I will consider a small area. And this is a small area, and assuming this is ds. So from here to here, that is ds, which means the dimension here. So for this small area, we have the dimension is ds multiplied with t, that is the area. So if we would know the small area multiplied with strain stress, that gives us the small force. Okay, so right now what I want to do is this. Across these circulations, the T is given. The application of the T will in certain way to distribute the influence of the T into every single element. So that means we take the influence of the small force, and on each of the segment we take the integral along the line path. And respect to certain center, that will give us the moment. The moment must be in equilibrium with the torque.
You're talking about area, right? When you
Area,
say
yeah. Okay. So with these things in mind, so what I want to do is this. We pick up any point, say O. So O is an arbitrary point. And just for us to take the information. So here I can find is the along this local point, I normal to the thickness, I draw the normal line here. So this is the normal line. Okay. So the small torque. So right now what I want to do is I take the moment about the O must be equal to T. The torque is given, and then that torque will produce the certain shear stress, and the shear stress must be in total, must be in equilibrium with the torque here. And that means here is the integration is this, the small force multiplied with certain distance. What is the distance? Yes. So for this case, let me call this is a distance called the P. I follow our textbook notation. The distance from here to here is called the P. So this one, small force multiplied with the distance that gives us a small torque. Right? And here we take the integral along the whole path. This is along the path of the cross section. Okay, hopefully you know. So that one must be equal to T. So this is again we take the equilibrium equations about the moment. In the property 1, we take the force equilibrium. In the property 2, we take the moment equilibrium. Okay, so right now we simply implement this one.
DF, is it that
DF is a small force. So basically here, let me
so that's an applied force?
No.
Like, or where are you getting this?
This small area,
yeah.
multiply with tau, will give us DF
Okay.
equal to tau times the small is T times ds, right?
Okay, yeah. Just making.
Okay, so with this one, so we can simplify this one. So that means df equal to tau times T ds, and this one multiplied with P, and we do the integral, and
And what is S standing for? Is that like arc? Like, because I know usually when we use
yes,
S, it's
S
arc
is the
Yeah.
small dimension here.
Okay.
Yeah.